All right, everybody, welcome back. Today we're doing relative velocity, kind of these advanced example problems. These are going to take a little bit of a while, but hopefully you're getting pretty comfortable with this chapter. So, a boat is traveling 12 meters per second north in still water when it encounters a current going 5 meters per second at 30 degrees north of west. Maybe we could just do this. 5 meters per second, and this is going 12 meters per second north of west. So this is west, this is 30 degrees. Okay. All right. If the boat does not change its steering, what velocity is the boat now going? So now meaning going with the current. So what we need to find out is how much the current is going to be going in the x and in the y. So this v sub x is going to be equal to, and this v sub y of the current, what is that going to be equal to? So I'm going to do, if I do 5 times cosine, whoops, if I did 5 times cosine of 30, that gives me the x. So that's going to be 4.33 meters per second. And then the Vy is going to be 5 times sine of 30, which I know is already just 2.5 meters per second. Okay, so I can just do this vector addition here. I'm going to just do the resultant vector. So the resultant in the x is going to be 0 because the boat's not going in the x at all. Plus the current's going to be pushing it, I'm going to say negative 4.33 because the current's going to be pushing it to the left 4.3. So I'm going to total negative 4.33 meters per second. And the resultant vector in the y, the boat's going 12 up, and the current's going to be pushing it 2.5 up, so that's going to be 14.5 meters per second. And now I'm just going to kind of draw this out, how this is going to look. It's going to look 4.33 here, and then 14.5 here. And then I'll use a different color for the resultant. This will be the resultant vector with the angle here. So this is going to find the velocity. So I'm just going to do the Pythagorean theorem here to find this. The velocity is equal to 14.5 squared plus 4.33 squared and the square root of that. So let me do that to my calculator. 14.5 squared plus 4.33 squared. Square root of that equals 15.13. So this velocity should be 15.13 meters per second. And this angle here, I'm going to use tan. So let me see. Tan inverse is equal to opposite 14.5 divided by adjacent 4.33. And the angle that's going to give us tan 14.5 divided by 4.33. That's going to give us 73.37 degrees. Okay, so I can say 15.3 at 73.37 degrees. And what's that going to be? North of west. Okay, so that's my answer for part 1. Okay, they did 106. So, another way of doing it is 106.63 degrees. Okay, moving on, part B. The boat has been riding the current for 15 seconds. How far is it traveling on the X and Y axis? Okay, so let me use a different color for this now. I'm going to use this. So this is part B. Okay, so good thing we need to know is we just need to break things up into the X and Y axis. So we should know that the total velocity in the x direction is going to be this negative 4.33 meters per second. And the total velocity in the y direction is just going to be 14.5 when it's traveling with the current. Okay, we know that it's going to be traveling in the x direction for 15 seconds. And it's going to be traveling in the y direction for 50 seconds. Time doesn't have a direction, so that's why it's going to be at both. And this way we can find how far did it go in the x direction and then how far did it go in the y direction. So let's do the x first. We should know that I'm going to say velocity in the x is equal to displacement in the x divided by time. So if we plug this all in, we have, I'm just going like this, velocity in the x is negative 4.33. How far has it traveled? Okay, so I guess I don't need to put negative because it's just asking for how far it traveled, not really the displacement. So I'm just going to erase that 4.33. It's going to be equal to the displacement, which we're looking for, divided by the time, which is 15 seconds. So I can say the displacement in the x direction is 4.33 times 15, and that gives me 64.95 meters. So that's x. For the y, we have velocity in the y, which is 14.5, is equal to displacement in the y, which we're looking for, time, which is 15. And now we can do displacement in the y is equal to 14.5 times 15, and we get 217.5. So as it's been traveling in the water for 15 seconds, in the x direction, it goes to the left 64.95 meters, and it goes up 217.5 meters. Okay. I guess they have a negative there. So if you wanted to have negative, that's fine. If you didn't, I also think that's fine because it doesn't specifically say. What is the displacement of the boat after being on the current 15 seconds? So great, displacement. So what this is asking for is just the combined value. We know how much it went in the x and the y, but let's find out now what that combined value is. So I'm going to do the x first. It goes 64.95 to the left. Oh, this isn't going to be to scale, but it's okay. It's going to go 217.5 up. And now for the resultant vector, or in this case, the displacement, I'm going to use a different color. This is displacement. And we're going to figure that out. Displacement also has direction. So displacement is, we're just doing Pythagorean theorem. 217.5 squared plus 64.95 squared. The square root of that. And we get squared plus 64.95 squared, square root 226.99 meters. Okay. But we also need the direction. So I'm gonna do tan for that. Inverse tan, opposite, which is 217.5 divided by adjacent, 64.95. This is gonna give me the angle. The angle is 217.5, oops, divided by 64.95, 73. Oh, it's going to be that same angle. And I should have known because the velocity and the displacement is going in the same direction. So the final answer is going to be 227 meters at 106.60 degrees, or we could say 73.37 degrees north of west. Okay. All right, hope that made sense. I know that one was a bit hard. Watch it back if it was hard, but also the next problem is similar, so just try to do the next problem. All right, so let's look at this. A boat is traveling 15 meters per second east in still water. It encounters current going 6 meters per second at negative 20 degrees. Let me try to change colors and figure this out. So this current is going 6 meters per second. And we have this negative 20 degrees, so it's like that. This boat is going 15 meters per second and encounters this current. Okay. If the boat does not change its steering, what velocity is the boat now going? Okay, so with the current, how fast is it going to be going? So similar thing, let's kind of just figure out what the velocity of the current is in the x and the y direction first. So I'm going to, for the x, I'm just going to do 6 times cosine of 20, and I get 5.64. And then for y, I'm just going to do 6 times sine of 20, and I get 2.05. That's going down, so we're going to have to just remember that. That's like a negative. Okay, so part A. Let's see. Part A. How we're going to do this. So let's find what the total velocity is in the x direction. So I'm just going to do the resultant in the x is going to be 15. That's what the boat's going before it finds the current. And the current's going to be pushing it in the x direction, 5.64. So this is going to be 20.64. Okay, meters per second. And then for the y, the boat isn't going in the y direction at all, 0, but it's going to be the current's going to be pushing it down negative 2.05, so it's going to be pushing it down negative 2.05 meters per second. Okay, now so we could use some vectors. So we have 20.64, and then we have 2.05. That goes down. Now let me use this. So the resultant vector, or the velocity, is this right here with the angle. Okay, so we can find the velocity. We can just do 20.64 squared plus 2.05 squared, and the square root of that. Let's see what that is. Squared plus 20.64 squared. And we get 20.74. So the velocity is 20.74 meters per second. And now let's find this angle here. I'm going to do tan. So inverse of tan is opposite, which is 2.05, divided by adjacent, which is 20.64. This will give me the angle. Whoops. And the angle is inverse tan, opposite 2.05 divided by adjacent 20.64. And we get 5.67 degrees. Okay. So we should know that the velocity is going to be 20.74 meters per second at, I'm going to just say negative 5.67 degrees. Or you could say 5.67 degrees south of east, whichever one is better for you. Okay. Okay. Part B. Let me change colors. What is the displacement of the boat after being on the current for 10 seconds? Okay. So to find this, how can we do this? I guess there's a few ways you can do this. We could find what we know in the x and y direction, and then find what the displacement is in the x and displacement is in the y. However, I don't think I'm going to do it that way. What I know is I already know the velocity that it's going in, and I know direction it's going in, so I can just use that to find the displacement. So I know that the velocity is like this way, and it's at an angle of this negative 5.67 degrees. So I just have to calculate that for 10 seconds. So velocity is equal to 20.74 meters per second. The time is equal to 10 seconds. And we want to know how far it travels in that time. So we know velocity is equal to displacement times time. Now we can do 20.74 is equal to displacement, which we're looking for, divided by time, which is 10. And now we can say that the displacement is equal to 207.4 meters. But remember, displacement always also accounts for direction, but it's going in the same direction as this velocity because that's the way it's moving. So that's going to be at negative 5.67 degrees. Okay. All right. I hope that made sense. Last problem over here. It's a little bit of a mind bender, but so take your time if you don't want to see the problem. I don't think it's too hard, but it is. You do have to think outside the box a little bit. A passenger on a boat notices that rain is falling vertically just outside the window. When the bus moves with a constant velocity of 18 meters per second relative to the ground, the passenger observes that the falling raindrops are now making a 15-degree with respect to the vertical. Find the speed of the raindrop relative to the ground. Okay, so pause if you want to do this for yourself, but most of you are going to be like, "What's going on?" Which is fine. But let me try to just explain what's going on. So when the bus is not moving, so this is the bus, it's not moving. The raindrops look like they're just falling straight down like this. Okay, and you might have noticed this in real life, but when the bus is moving, so when the bus is moving, and I guess it's moving at 18 meters a second, the raindrops now look like they're going like this. So it's not that, oh, wind picked up or anything like that. It's because you're moving. That's why the rain now looks different to you. And just like in this picture here, we can see that these raindrops are at an angle. Okay, and that angle is 15 degrees. Okay, so find the speed of the raindrop relative to ground. So okay, what we know, and I'm gonna just dramatize these raindrops, is as we're going towards these raindrops, it's going to look like this. And what we should also know, I'm gonna change the color, is the angle that it makes. I'll do it with this one. Is 15 degrees. Okay, I'll just erase the other ones for now. Okay, so what we should know is this. Okay, so this is the raindrop that's going like this. Okay, and what we should know is that that side right here, this is how fast the raindrop is going to be going in the x direction when we're looking at it. And that's going to be equal to 18 meters per second. And the reason for that is because when we're not moving, it's not moving in the x direction at all. However, when we're going towards it, what's happening is the raindrops is appearing to be moving towards us, but what it's actually doing is it's just going towards us because we're just moving towards it. So however fast we're going towards it, that's how fast it's going towards us, which is this 18 meters per second. Okay, and so when we're looking for the speed of the raindrops relative to the ground, we're looking for how fast these raindrops are going because the ground isn't moving. So we're looking for how fast are those raindrops are going, which is equivalent to this line right here. So we can use tangent to find that. We could do tan of 15 is equal to opposite, which is 18, over adjacent, which is this velocity of the raindrops in the right y direction, also what the velocity of the how fast the raindrops are going hitting the ground. I know that might probably sound a little bit confusing, but maybe watch it again. It is a little confusing, but this is how you do this problem. And maybe this is also why this is the last problem. Anyway, the final answer is it's going to be hitting the ground at 16.18 meters per second. All right, guys, I hope you enjoyed this chapter, this unit. Next time, we're going to be doing projectile motion. Thanks for watching.